sklearnneighborsBallTree. Description: the BallTree class in scikit-learn implements a BallTree data structure for efficient nearest neighbor search in multidimensional spaces. It partitions the data points into a hierarchical tree, where each node represents a region ball in the feature space. The tree is constructed recursively by dividing the data points into two subregions based on the distance to the center of the ball. This partitioning continues until the number of points in each region is below a certain threshold. Inputs: X, a 2D array of shape n samples. N features representing the data points for which the ball tree will be built. Each row corresponds to a data point, and each column represents a feature. Metric: a string or callable object specifying the distance metric to use for calculating distances between points. The default is Minkowski, which corresponds to the Euclidean distance. Other options include Manhattan, Chebyshev, cosine, etc. Outputs: self, the ball tree object itself, which can be used for subsequent nearest neighbor search operations. Steps: construction: the ball tree is constructed based on the provided data points and distance metric. This involves recursively partitioning the data points into balls until a certain threshold is reached. Search: once constructed, the ball tree can be used to find the nearest neighbors of a given query point. This is done by traversing the tree, starting from the root node and recursively checking the balls that are closest to the query point. Metrics: distance metrics: the ball tree supports various distance metrics, allowing users to choose the most appropriate one for their data and application. Common metrics include Euclidean distance, Manhattan distance, Chebyshev distance, and cosine distance. Visualization plots: ball tree structure: the ball tree can be visualized as a hierarchical tree structure, where each node represents a ball containing data points. This visualization can be helpful in understanding the partitioning of the data space. Fine-tune parameters: leaf size: the maximum number of points allowed in a leaf node. Smaller leaf sizes can lead to more accurate results but may increase construction time. Metric params: additional parameters to pass to the distance metric function. Uncertainty methods: nearest neighbor distance: the distance to the nearest neighbor can provide an indication of a uncertainty in the prediction. A larger distance suggests greater uncertainty. Challenges and fixes. Challenge 1: high dimensionality. For very high dimensional data, the performance of the ball tree can degrade due to the curse of dimensionality. This can lead to inefficient search times. Sample use case that resulted in challenge 1: a dataset with hundreds or thousands of features may experience slow nearest neighbor search due to the increased complexity of the ball tree. Fixes to challenge 1: dimensionality reduction techniques like principal component analysis (PCA) or feature selection can reduce the number of features, making the ball tree more efficient. Approximate nearest neighbor search algorithms like KD tree or random projection can be used to find approximate nearest neighbors, which can be faster for high-dimensional data. Challenge 2: memory usage. The ball tree can consume significant memory, especially for large datasets. Sample use case that resulted in challenge 2: a dataset with millions of data points may require a large amount of memory to store the ball tree structure. Fixes to challenge 2: memory-efficient data structures compressed as sparse representations of the ball tree can reduce memory usage. Out-of-core algorithms. Algorithms that operate on data that is stored on disk rather than in memory can be used to handle large datasets.